So 3.1, lesson 3.1 was using the first derivative as a means of finding intervals which the function is increasing or decreasing. It had to do with the slope of the tangent line. If the first derivative yields positive value, that's a positive slope of the tangent line. That's an increasing interval of the function. And if the first derivative yielded negative values, that was indicative of a decreasing interval. So we take the first derivative, which is equal to 3x squared minus 24x. Okay, now we need to set the first derivative equal to 0 to find critical values. So 0 is equal to 3x times x minus 8, which means the critical values are x equals 0 and x equals 8. Okay. Now on a number line, we test values in each interval broken. The number line places the critical values on the number line, test points within each interval into the first derivative to see if it yields positive or negative values. So we could test f prime -1, we could test f prime of +1 in this interval right here, and we could test f prime of 9. Okay, it doesn't matter the actual value that it yields, just matters whether it's positive or negative. So if we plug a -1 into the first derivative function, this form of it might be a little bit easier. 3 times -1 is a negative value. -1 minus 8 is another negative value. Negative times a negative is going to yield positive. Okay, now testing f prime evaluated at x equals 1. 3 times 1 is a positive value, but 1 minus 8 is still a negative value. Positive times a negative is negative. Then f of 9, 3 times 9 is a positive number. 9 minus 8 is another positive number. Positive times a positive, positive. What this means is any number that we would have chosen in this interval plugged into the first derivative function is going to yield a positive value. That means the function is increasing on this interval. Okay? Increasing on the open interval -infinity to 0, and there's another interval right here from 8 to infinity. This region that's negative right here is where the function is decreasing. That means that the tangent lines in that interval are going to have negative slopes because the function is decreasing. So it's decreasing on the interval 0 to 8. Question 4 and 5 actually come from 3.2. I've mislabeled the review. These two are from 3.2. The first derivative test to find relative extrema. This is where the graph has a relative minimum or a maximum. Okay, we find the first derivative, set it equal to 0 to find critical values, and then decide using the first derivative test whether or not they're relative minimums or relative maximums. So the first derivative, this function, if you use a simple power rule here and take the derivative of each of these terms, 4 drops down in front, 4 times 1/4 is 1, so this is x to the third minus 8. If we set that equal to 0, we can add 8 to both sides, and we have 8 is equal to x to the third. Now we can get rid of the power 3 by using the cube root. And the cube root of 8 is equal to 2, so the critical value here is x is equal to 2. Now, this is a critical value. We don't know whether it's a relative minimum or a maximum, so we use the first derivative test. We choose numbers now in each interval plugged into the first derivative, so f prime of 1 we could test, and f prime of 3. Now when 1's plugged into the first derivative, 1 cubed minus 8 is a negative number, but if 3 is plugged into the first derivative here, 3 cubed minus 8 is a positive number. Now how we read this graphically is in this interval the function is decreasing, so it may look something like this, where it's decreasing, but when it reaches x equals 2, then the function starts to increase. Because of that behavior, where it switches from a decreasing to an increasing function, it has to be a relative minimum. So there's a relative minimum when x is equal to 2. Now the actual point that represents that on the graph, we have to plug a 2 as an input into the original function here for both x's. 2 to the 4th power is 16. 1/4 of 16 is 4. 4 minus 8 times 2 is 16. This is 4 minus 16, which is negative 12. So the minimum value is negative 12 when x equals 2. Now question 5, this comes from the same section. These are both from 3.2. It's the same thing, just a different type of function to give us a little more practice here. H prime of x. Now we have to take the derivative of a quotient. We use a quotient rule, which is, if you remember that phrase, low d high minus high d low. So it's the bottom function, x minus 2, times the derivative of the top function, 2x, minus the top function times the derivative of the bottom function, all over the square of the bottom function. Simplifying the numerator, we're going to have a 2x squared minus 4x minus x squared over x minus 2 squared. And simplifying one more time, we're going to have x squared minus 4x all over x minus 2 squared. Now, critical values, normally we've been finding them by setting the first derivative equals to 0, and that's still going to work here, but the other part of it is we can also have a critical value when the first derivative is undefined. Because we have a rational equation here, it's going to be undefined at this value when the denominator is equal to, when the denominator becomes 0, and to do that we have to have an x value of 2. So there are more critical values than you might think. X equals 2 is a critical value because it makes the expression undefined, or the first derivative undefined. Now we have to find out where the first derivative is equal to 0. Because it's a rational expression, it's only ever going to equal 0 when the numerator here is equal to 0. So there's two values of x that will make the numerator equal to 0. It's x equals 0 and x equals 4. So those are three critical values that we have. So if we test those, 0, 2, 4. So now we need to choose test points within each interval, plug them into the first derivative, see what comes out of that. So we need to test h prime of negative 1. We could test h prime of positive 1. We could test h prime of 3 and h prime of 5. We got to figure out what's happening with all these. So if we look at a negative 1, negative 1 squared is positive. Negative 4 times negative 1 is positive. And a positive, so we have a positive in the denominator, or in the numerator. Now, this denominator is being squared, so regardless of what happens in the parentheses, squared it always becomes positive. So the denominator will always yield something positive. Positive divided by a positive is a positive interval. Now, h prime of 1, if we plug a 1 in, 1 squared is positive. Minus 4 times 1, though, makes it negative. So we have a negative divided by something that's always going to be positive down there, so that's a negative interval. Plugging in a 3 for both x's here. 3 squared is 9, but minus 12 here makes it negative. Negative divided by positive is negative. And if you plug in a 5, 5 squared is 25, but minus 20 makes it positive. Divided by a positive is positive. So even though we have three critical values, only two of them actually are going to yield a local or relative extreme. And it's when the graph changes from an increasing to decreasing, such as right here, or decreasing to increasing, such as right here. So that critical value and that critical value are actually local extreme. Now, it depends on the behavior of the graph, whether or not it's a local min or a local maximum. So here, it's changing from an increasing function, so the function is increasing, but then at x equals 0, it starts to decrease. So that has to be a minimum, or a maximum, right? So there's a maximum when x equals 0. Then here, because it's switching from a decreasing function to an increasing function, okay, when x equals 4, we have a minimum. And then we have to plug these values in to the original function here to figure out the point on the graph. So when x equals 0, h of x is equal to 0. So that point is 0, 0. When you plug a 4 into the original function, 4 squared is 16, and 4 minus 2 is 2, 16 over 2 is 8. So the point is 4, 8. Question 6 is also from 3.2. This was labeled incorrectly. That should be a 3.3. Talked about concavity. Anyway, question 6, find the absolute extreme. Okay. This is a similar process, but now also have to consider the endpoints as being one of the extreme values of this closed interval, not just the critical values. So we have to find the first derivative, set it equal to 0 to find the critical values. So again, using the product, or the quotient property rather, it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Simplifying in the numerator is going to yield a -2, and then it's all over x minus 2 squared. Now, we can have a critical value, remember, whenever the first derivative is equal to 0, or when it's undefined. It's undefined when x equals 2, and because there are no x values in the numerator, this expression will never equal 0. So the only critical value we have is x equals 2. Okay? But we have to consider the interval on which we want to find extreme values. The critical value does not lie within the interval 3 to 5. So we're not going to consider it as a possibility as giving an extreme value. All that leaves are the two endpoints. So 3 and 5 are going to yield, one of them is going to yield a local minimum, or an absolute minimum. It will yield an absolute maximum. We just have to evaluate them in the function, original function, to see which one has the highest value. If a 3 is plugged into the original function, 3 over 3 minus 2 is 3. Plug in a 5, 5 over 5 minus 2 is 5/3. This one has the highest value. So 3, 3 is the absolute maximum in my closed interval. And the point 5, 5/3 is the absolute minimum value. That brings us to 3.3, where we talk about concavity and the second derivative test. They're performed similar to the first derivative test. So in question 7, we start with the first derivative, which we find the second derivative and set that equal to 0 to find points of inflection. Points of inflection are where the graph switches from concave up to concave down, or vice versa. That's the second derivative. If we set this equal to 0 and factor out a 12, and then factor using difference of squares, we can see that the two points of inflection here, or the two x values that make the second derivative equal to 0, are x equals 1 and x equals -1. So now this test looks like it's similar to the first derivative test. It is. It's the second derivative test though, and it describes the concavity of the graph. So we test points within each interval into the second derivative. So we do f double prime of -2, for example, f double prime of 0, and f double prime of 2 to see whether or not we have positive or negative values in the second derivative. So if a -2 is plugged into the second derivative, we have here -2 squared is 4, -1 is 3 times 12, that's a positive value. But if 0 is plugged in, 0 squared is 0, -1 is negative times 12, it's a negative value. And then here 2 squared is 4 minus 1 is 3 times 12, it's a positive value. Now, in the second derivative test, a positive interval doesn't mean that the graph is increasing. What that means is the graph is concave up, it's curving upwards like this. So the intervals f of x concave up on the interval negative infinity to negative 1, and there's also another interval here, union 1 to infinity. And f of x is concave down on the interval negative 1 to 1. Okay. Question 8 is a similar thing. We have to discuss the concavity of the graph using the second derivative test, and then we have to actually find the points of inflection. Pretty much the same thing we did. The derivative here is a little bit more tricky. The second derivative is a little trickier to find. It's a product property with a chain rule, a little bit of a chain rule in there. So start with the first derivative, h prime of x. Now these two are forming a product. Remember the product property. If h of x is the product of two separate functions, f of x times g of x, and the derivative is f prime of x times g of x plus f of x g prime of x. That's the product property. So applying that here, we take the derivative of this first part of the function, which is going to be 3 times x minus 1 squared, and since it's a function within a function, we have to do a chain rule, do the derivative of the inside, which just happens to be 1. And we multiply that by the second function, x minus 5. And then we add the first function times the derivative of the second function. Now, there's a lot happening here, but really we need to consider this as a term added to this as a term. And if we consider both terms and what they have in common, they both have an x minus 1. This one has an x minus 1 cubed, this one has an x minus 1 squared, so they both have at least an x minus 1 squared that can be factored out. So if x minus 1 is factored out from this part of the first derivative, so this x minus 1 was factored out, what that leaves is 3 times quantity x minus 5, which becomes 3x minus 15. Now, from this part, if we factored out x minus 1 squared, that just leaves an x minus 1. Simplifying a little bit, inside of there gives us 4x minus 16. That's the first derivative. Now if we do the second derivative, similar technique, we're going to have to do a product property. So the derivative of the first, and then a chain rule, we have to multiply by 1 times the derivative times just the second function plus the first function times the derivative of the second. Now if we start to simplify this part of it, 2 times x minus 1 is 2x minus 2, and if we times it by 1, it still stays 2x minus 2. Now if we multiply these two together, we're going to get 8x squared minus 40x plus 32. Now if we multiply these two together, first of all, x minus 1 to the second power is x squared minus 2x plus 1. We multiply that by 4, we get 4x squared minus 8x plus 4. Combining all the like terms, we're now going to have 12x squared minus 48x plus 36. This is the second derivative of h. If we factor out at 12, we have x squared minus 4x plus 3, which factors into x minus 3 times x minus 1, and that means h double prime of x is equal to 0 when x equals 3 and when x equals 1. So those are the points now that we have to place on the number line. To discuss the concavities, we have 1 and 3. Test points in the intervals now. In the second derivatives, we need to do h double prime For 0, we can do h double prime. For 2, I do h double prime. For 4, so when when we plug in a 0 to the second derivative of h, 0 minus 3 is negative, 0 minus 1 is negative, negative times a negative times 12 is positive. 2 minus 3 is negative, but 2 minus 1 is positive. Positive times a negative times 12 is negative. And then 4 minus 3 is positive. 4 minus 1 is positive. Positive times a positive times 12 is positive. We have a region now where we know the graph is going to be concave up here and here. So h of x concave up on the intervals negative infinity to 1 and 3 to infinity, and it's concave down on the interval 1 to 3. Now we know where the graph switches from concave up to down and down to up. We actually need to state the points of inflection, so we know that it's 3 comma something and 1 comma something. So 3 plugged in, 3 minus 1 is 2, 2 cubed is 8. We have an 8. 3 minus 5 is negative 2. 8 times negative 2 is negative 16. If 1 is plugged in, 1 minus 1 is 0. 0 cubed is 0. 0 times anything over there is going to be 0. And these are the points of inflection.
Okay, question 9. We're trying to discover the graphical relationship here between an original function here, f of x, and without knowing what the equation is, we need to come up with a graph over here of what we think the derivative is going to look like. And this uses almost everything we've learned in Unit 2, increasing and decreasing, extrema, concavity. So if we take a look at the original function on this interval, for example, that I'm highlighting, excuse me, that part of the graph is increasing. And if you remember, an increasing part of the graph is where the derivative, the slope of the graph is positive. So the derivative would be greater than 0. So this portion of the graph right here that I'm highlighting in black, since that's an increasing part of the original function f of x, this is where f prime of x would be positive. And so if you look at part A, we need intervals on which f prime is positive. Well, this part of the graph right here is increasing. Also, this part of the graph right here that I'm highlighting, that part of the graph is increasing. So to answer part A, we could say f prime of x is positive or greater than 0 when, so if we come back and look at what interval that is right there, what x values, which x values are used in that part of the graph. Now let's see, get my eraser here so we can get a better look. Looks like if we say that's the top of it right there, it goes from negative infinity to about negative 1. And then this other part of the graph here, let's say it's about right there where x equals 2. So then also from about 2 to infinity. So from negative infinity, I'm going to highlight it here again, from negative infinity, here it is right here, from negative infinity to negative 1, and also from 2 to infinity. Those are increasing parts of the graph, which means the derivative f prime of x is going to be greater than 0. Now to answer part B, we need parts of the graph that are decreasing. So this part right here, where x is between negative 1 and 2, that's a decreasing part of the graph. If you remember, decreasing part of the graph means the slopes of the tangent lines are negative. Also, f prime is going to be negative. So to answer part B, we need to describe this piece of the graph right here. So that part of the graph, f prime of x is negative or less than 0 when x is between negative 1 and 2. Now, part C right here, let me erase some things on the graph. Part C, when is f prime of x increasing? F prime of x increasing. Well, f prime of x increasing means the rate of change is increasing. So we need the rate of change of f prime. And if you recall, rate of change is a derivative. If we took the derivative of f prime, we would get f double prime, or the second derivative. So what we're talking about with the second derivative is concavity. So if you remember from section 3.3, when we talked about the second derivative on concavity, if the second derivative is positive, the graph is concave up. Wherever the second derivative is negative, the graph is concave down. So if we go back to the picture of our original function and consider the graph from about here to about right here. So if we consider this piece of the graph from there to there, that piece of the graph is concave down. And then change colors here. This piece of the graph, starting about right here to here. This red part of the graph that I've highlighted, that's concave up. So the red part of the graph, concave up, that means the second derivative is positive. Remember, concave up means the second derivative is positive. If the second derivative is positive, that means f prime of x is increasing. So f prime of x is increasing wherever the second derivative is positive, and the second derivative is positive right here on this concave up part of the graph. So for part C, I could say f prime of x increases when f double prime of x is greater than 0, and that happens if we look at the graph. It switches concavity about right here. We can call that an inflection point. So f double prime of x is increasing where the graph is concave up, and that looks to be on the interval from 0 to infinity. And then for part D, f prime of x decreasing. F prime of x decreasing means the rate of change of f prime is decreasing. The rate of change would be a derivative. So again, we need to look at the second derivative. Wherever the second derivative is negative, so let me write this down for part B. So f prime of x decreases when f double prime of x is less than 0. Again, if you remember from section 3.3, the second derivative is less than 0 means the graph is concave down. So this piece of the graph right here is concave down. That's the interval negative infinity to 0. Okay. Now, even though they don't ask for it, some other useful pieces of information. Let me go ahead and erase this from the original function. They don't ask for the extrema, but it's useful to point out we have a relative maximum here when x is -1, and just for the sake of having nice numbers to work with, I'm going to call this one 2. There's a relative minimum at 2. If you recall from section 3.2, when we talked about extrema occur when the slope of the tangent line is 0. So we have a horizontal tangent line here, and we're going to have a horizontal tangent line there. Okay. Remember, the horizontal tangent line means the slope is 0, or the derivative is 0. So when x is -1, this is where we're going to start transferring things from f of x graph over to f prime of x. So when x is -1 right here, that means the derivative is 0. So at -1, on my f prime, I'm going to put a 0. And the same thing here, when x is 2, the slope of the tangent line is also 0. So here, when x is 2, I'm going to say it's 0. Now we can use these answers here to help us with the graph, because we're graphing f prime of x, and part A, B, C, and D describe behaviors of f prime of x. For example, part A says where it's greater than 0. F prime of x is greater than 0. What that means, greater than 0 is going to be above the x-axis. So f prime of x is above the x-axis from -∞ to -1, and also from 2 to infinity. So from -∞ to -1, it's above the x-axis, and from 2 to infinity, it's above the x-axis, so it may look something like that. Those are both above the x-axis. And between -1 and 2, it's below the x-axis. It's f prime of x is less than 0. Okay. And then for part C and D, well, let me finish with part B. To be below the x-axis, looks like we're going to have a little piece that dips down, like that. Okay. And then let's just make sure our graph fits with the description in part C and D. F prime of x needs to be increasing when x is 0 to infinity right here. So from 0, if we're looking at 0 to be about right there, from 0 to infinity, the graph f prime of x is increasing, like part C says. And then part D says f prime of x needs to decrease from -∞ to 0. So -∞ to 0 is talking about this part of the graph, and it is indeed decreasing till about 0. So it looks like we have a pretty good sketch here of f prime of x. One other thing to keep in the back of your mind, the original function f of x looks to be some kind of an x to the third type of graph. That's a typical shape of a cubic graph. If we were to take the derivative of an x to the third function, we would end up with an x squared graph, or a second degree polynomial. So if you take a look at our f prime of x here, we've graphed a parabola, which is a typical graph for a second degree polynomial.
Okay, the point of diminishing returns, this was part of 3.3's lesson, the latter part. The point of diminishing returns is a point of inflection of a graph when it switches from concave down to concave up. That means it's still increasing, but just it starts to increase at a slower rate. That's a point of diminishing returns. So what we need to do is find the second derivative of this. I'm just going to simplify this. So this is -2/3 x to the third, and then -2/3 times -12 is going to be positive. 3 goes into 12 4 times 2 is 8, so this is 8x squared, and then 2/3 of 6 How many thirds are there in 6? That's one way you could think about it. Or 3 goes into 6 twice, times 2 is 4, so this is plus 4. So this is what r is equal to. R prime then is negative 2x squared plus 16x. And second derivative is negative 4x plus 16. Now this is going to equal 0 when x is equal to 4. Now first let's just check that's in the specified domain. X can be anything between 0 and 8, where 8 is in thousands. These are in thousands of dollars, so this represents a value of $4,000. Now, just to check that this really is a point of diminishing returns, we have to check that the graph is switching from concave down to concave up. So in the second derivative, we can test a 3 and we can test 5. So plugging a 3 into the second derivative, plugging a 3 into the second derivative here, negative 4 times 3 is negative 12 plus 16 is positive. And then 5, negative 4 times 5, negative 20 plus 16 is negative. This is a point of inflection. The graph is switching from a concave up. No, it's a concave down, right? Concave up type of a graph. And then when it reaches x equals 4, it starts to change to a concave down. So right there in the middle, that's the point of diminishing returns. The rate is increasing much faster than the rate is increasing over here. This has a steeper tangent line than the tangent line on this side. So even though they will still be making more money on by spending more money on advertising, they're not going to be making as much at the same rate as right here, the point of diminishing returns. So spend $4,000. That's the point of diminishing returns. Spend $4,000 on advertising. Okay. So what we're trying to optimize here is the perimeter. So the perimeter formula for a rectangle is 2L plus 2W. Now to optimize or to minimize or maximize any function, we take the derivative. The problem is this is not a function of one variable, this is a function of length and width, which is really going to complicate things. So what we need is a secondary equation. We have some information here that the area, which is length times width, is equal to 225 square meters. So if we divide by one of the dimensions, it doesn't matter, we can divide by L on both sides. That yields width in terms of the length. Width is equal to 225 over L, which also means this width right here is equal to 225 over L. So the perimeter function can be written in terms of L, 2L plus 2 times 225 over L, which is 2L plus 550 over L. So the derivative is 2 minus 550 over L squared. Now, if we set this equal to 0, we're going to add this term to the other side. Now there's a couple different ways you could solve this. You could think about this as a fraction. 550 over L squared is equal to 2 over 1. This is what's called the proportion where we have a fraction that equals a fraction. One way you can solve a proportion is by cross multiplying. So multiply those together and set them equal to each other. We're going to have 2L squared is equal to 550, which means that L squared is equal to 225. You square root both sides, and L is equal to, I mean technically it's plus or minus 15, but because these actually represent lengths and widths of rectangles, we consider the feasible domain, which is positive numbers. So the length is equal to 15. Now, we do have to check that this actually is a minimum value here, and not a maximum, so using a quick little first derivative test, 15, we test points in each interval on either side of 15. So if we plug in a 14 over here for L, 14 squared is 196. Now 550 divided by 196 is a little bit more than 2. If you take that from 2, you end up with a negative value. So 16 squared, let's see, 16 times 16. Looks like that's going to be 256. Now, if you take 550 divided by 256, that's a little bit less than 2. So if you take that from 2, you end up with a positive value. So this means is the graph is switching from a decreasing function to an increasing function, which proves that this is a minimum. So when the length is 15, we've got to go back and find out what the width is. The width is equal to 225 divided by the length, but if the length is 15, 225 divided by 15 is also 15, so the width is equal to 15. So the length and width of a rectangle with minimum perimeter is a square. Okay, so I would recommend drawing this one out. We have an indoor physical fitness room that's a rectangular with semicircle. Semi means half of a circle on each end. The perimeter, so just measuring around the room like this, if somebody were running around, that's 200-meter running track. Find the dimensions that will make the area of the region as large as possible. So we're maximizing the area of this rectangular region inside. So we can say from here to here, we can say is x, and from here to here, we can say is y. So the area is equal to x times y of that rectangular region. Problem is, if we take the derivative on both sides, we have too many variables on this side. So we need a secondary equation. So it says the perimeter of the room. Now, the perimeter are these two sides of the rectangle. This, let me do this in a different color. It's this side of the rectangle and that side of the rectangle. So the perimeter of 200 is equal to 2x, but then it's also this top half and the bottom half. So it's actually a full circumference of a circle. And the diameter of that circle is y. Now the circumference of a circle is pi times the diameter. So we have plus pi times the diameter of y. So this is the perimeter. Now we just need to solve it for one of the variables. If we wanted to solve for x, for example, we could subtract pi y. So we have 200 minus pi y is equal to 2x. Then we can divide everything by 2. Now we have area, and now we know what x equals. X equals this value right here. So this is 200 minus pi y all over 2 times y. And this is equal to 200y minus pi y squared all over 2. Now we need to take the derivative. Now this might be easier to do one more little simplifier. If we separate, instead of dividing everything by 2, dividing separately by 2, we have 100y minus pi over 2 y squared. That might be a little bit easier to take a derivative. So a prime is equal to 100y, or 100 rather, minus pi times y. So if we set this equal to 0, that means that 100 equals pi times y, divided by pi, and y equals 100 over pi. That's this part right here, 100 over pi. Now, to find x, x right here, if we wanted to again make this maybe a little bit easier, x is equal to 100 minus pi over 2 times y. But we know that y is equal to 100 over pi. Pi's cancel. 100 over 2 is 50. 100 minus 50 is 50. So this has a length of 50 meters. So 50 meters here, 100 over pi meters on that dimension. Okay, question 13. Find the number of units x that produces the minimum. So right here, this means we're going to be optimizing using a derivative somewhere to find use the first derivative test. But what we're minimizing is the average cost. We've been given a cost function. The average cost, c bar, is equal to c over x. So c bar is equal to this whole expression pretty much divided by x, but it's going to make the derivative easier to divide every term separately by x. This becomes 0.2. Now x squared over x is x, and then 10x over x is 10, and 45 over x If we take the derivative, we're going to get 0.2 minus 45 over x squared. If we set this equal to 0, so if this were equal to 0 now, I'm going to add this term to the left side. It becomes 45 over x squared equal, now 0.2, I'm going to turn that into a fraction, it's 1/5, because 0.2 means 2/10, which is 1/5. Now, again, this is a proportion, it's two equal fractions, so we can solve by cross multiplying is one technique. We have x squared is equal to 45 times 5, which is 225. Square both sides to get x equals 15, and again, we're only considering the positive. The feasible domain for this problem is x has to be greater than or equal to 0 at least, because you can't produce a negative number of a commodity. So we do have to just show that this is indeed a minimum value. So if we were to take 15 and then we could find c bar prime of 14, for example, and c bar prime of 16, and see what's happening here. So if we plugged in a 14 squared at 45 over 196, if you take that from 0.2, that's going to result in a negative value. C bar prime of 16 would result in a positive value. Excuse me. So it means the graph is decreasing on that interval, but now it's increasing on that interval, so it does indeed, this relative extreme here is a minimum. Okay. And the question was asking find the number of units X that produces the minimum average cost. It wasn't asking for the actual average cost. So X equals 15 is the answer. Okay, 14 is going to take a lot of work. It's asking what price per unit will yield the maximum revenue. The problem is they didn't give us a price function or a revenue function in here. The revenue is equal to X, the number of units sold, times the price that they were sold for. Okay. Now, this price function I'm talking about here is the demand function. This is what we talked about on Monday, October, or on Thursday, Tuesday, October the 1st. The demand function is lowercase p, and it's a function of X, where X is the number of units. And if we assume that the demand function is linear, that means it's going to be a straight line with a slope. Now the way demand function is set up on a graph is the vertical axis here is the price, and the horizontal axis is the number of units. So the price is represented by lowercase p, number of units is X. So if we try to form ordered pairs from this number, for example, this is an X value because it's the number of units. This is a price value. So we form that into an ordered pair, X comma P, the point becomes 300, comma 40. If you try to form this statement into an ordered pair, the price went up $5, that's a price of $45, and they only sold 275 units, so that's 275, comma 45. Now, the slope between these 2 points is the change in y, which is, if we call this y2 and this one y1, the change in y is negative 5, divided by the change in x. 300 minus 275 is 25, so that yields a slope of negative 1/5. Now the price function is linear, so it's of the form y equals mx plus b, so we know the slope is negative 1/5 x, but we don't know its b value, so we can choose one of the points and use it as x comma p. So p can be replaced with 40, x can be replaced with 300. Negative 1/5 of 300 is negative 60. If we add 60 to the other side, b is equal to 100, so the price function p, lowercase p, becomes negative 1/5 x plus 100. Now that we know p, we can plug that in here to find the revenue function. So revenue is equal to x times negative 1/5 x plus 100, which is negative 1/5 x squared plus 100x. Now the derivative is equal to negative 2/5 x plus 100. If we set that equal to 0, I'm going to add this term to the other side. And end up with that. Multiply both sides by 5. You get 2x equals 500. Divide by 2, and x equals 250. Now we got to be careful on what we have here. Is this an answer? It's the answer to an equation. It's the answer to the question that was asked, though. X is the number of units. They're asking what price per unit will yield a maximum total revenue. Now, I guess technically we should just check to make sure this is a maximum value, but if we go back and look at the original revenue function right here, this is a quadratic function with negative leading coefficient, which means it's upside down, so it's an upside down parabola. So the vertex is going to be maximum value. This is the number of units you have to sell to maximize revenue, but what price are you going to sell it? So So now we have to refer back to the price function here. Okay, price is equal to negative 1/5 times the number of being sold plus 100. So negative 1/5 of 250 is negative 50. Negative 50 plus 100 means the price needs to be set at $50 to maximize revenue. And at that price, you'll sell 250 according to the demand function. Now, question 15, a little bit easier because the price function has been provided for us. The cost function is there. What price yields the maximum profit? Now, this is an uppercase P. Profit is equal to revenue minus cost. Now, revenue is equal to X times the price over here, so that's equal to X. So it's 36 minus 4X, which is negative 4X squared plus 36X. So the profit is equal to negative 4X squared minus, or plus 36X minus the cost, which is 2X squared plus 6. So combining like terms, we're going to have a negative 6X squared plus 36X minus 6. Now to maximize profit, we need to take the first derivative of the profit. So it's going to equal negative 12x plus 36, which is going to equal 0. Okay, so that equals 0 when equals 0 when x equals 3. This represents a number of units, but again they're asking which price yields the maximum profit. So they have to sell 3 units to receive maximum profit. What price is that? Well, if we plug a 3, so plug this value into the price function there, 4 times 3 is 12, 12 from 36 is 24. So lowercase p price is $24. Now, what is the average cost? So C bar is equal to C over X. This is equal to 2X squared over X plus 6 over X, which is 2X plus 6 over X. Now we know when the profit is maximized, they're selling 3 units, so the average cost of 3 units is 2 times 3, which is 6, plus 6 over 3, which is 2. That's $8.
Okay, question 16. The phrase at the end, what dimensions will use the least amount of fencing? In other words, what's the minimum amount of fencing to be used, but still have 245,000 square meters of area? So this is an optimization problem. We got some river here with the pasture. Now it's supposed to be rectangular, so this side here and this side here are supposed to be the same length. That's one of the properties of a rectangle. Let's call that X. Now the amount to be optimized is perimeter. This is the equation, this is the primary equation. Perimeter for P equals X plus 2Y. That's the perimeter of this rectangular area. Problem is, with this primary equation, we have too many variables. We have X and Y. So often in an optimization problem, you've got to create a secondary equation. Now it says the pasture must contain 245,000 square meters. So that's an area. So we have X times Y, that's the area of a rectangle, equals 245,000. If we get Y by itself, divide by X, you get 245,000 over X. So now we can take this and plug it in for Y and create a new perimeter formula. P equals X plus 2 times that area formula, 245,000 over X. I'm simplifying this a little bit. So there's a new formula for perimeter. It's in terms of just x. Once it's in terms of all the same variable, you can take the derivative. So we're going to take the derivative with respect to x. So we're going to get p prime equals 1. Now, this here, might be easier to move the x up to the top and think about it as 490,000 times x to the negative 1. So when you take the derivative, remember the negative 1 will drop down, making that a negative 490,000. And it would decrease the exponent by 1, so it would now be a negative 2. So you're going to get negative 490,000 all over x squared. So there's the derivative of the perimeter. Now because this is an optimization problem, we want to find a minimum or a maximum. So remember the way to do that is to set the derivative equal to 0, find the critical values, test them to see whether it's a min or a max. So I'm going to add this expression here, the 490,000 over x squared, to the right side and get 1 equals that. Then multiply both sides by x squared to get x squared equals 490,000. Take square root on both sides and get x equals 700. Now, technically it's plus or minus 700, but since x represents the width of this rectangle, it doesn't make sense to have negative 700, so we're just going to take positive. And we're supposed to test to make sure this is a minimum value, and we're trying to find minimum dimensions. So what you want to do is just do a quick number line check. Taking something to the left side of 700, 0, I know it's way down here, but if you tested 0, well, you can't test 0 because, let's test 1. Let's test x equals 1. 490,000 divided by 1 is 490,000. 1 minus 490,000, that's a negative value, so we've got negative. We tested something to the right of 700, like 1,000. 1,000 squared would be way bigger than 490,000. So we've got 490,000 divided by a very large number. That makes a very small fraction. 1 minus a small fraction is still positive. So we have a decreasing interval to an increasing interval. That means that 700, according to the first derivative test, is actually minimum. That's what we wanted. We wanted to find a minimum. So x equals 700. Now, we want to find the values of y, and we can use this equation right here, 245,000 divided by 700 gives you 350. So these are the dimensions we want to use in order to have minimum perimeter but maximum area, or not maximum area, but minimum perimeter that contains that area, 245,000 square meters.
Okay, question 17. We're doing infinite limits and limits at infinity. So 17 part A would be a limit at infinity. We're approaching here, x approaches infinity. What that means is x is getting larger and larger and larger. Graphically speaking, if we were taking a look at a graph, let me draw one here. If we were to draw a graph, x approaches infinity means, okay, x is just getting bigger and bigger and bigger. What's happening as x is approaching infinity? What's happening to the graph way out here? Now, that's a description of end behavior. End behavior on this type of a function, a rational function, end behavior of a rational function describes the horizontal asymptote. Where's the horizontal asymptote? That's the That's what a horizontal asymptote describes as end behavior. As x gets increasingly large in the positive or negative infinite direction, what value is y approaching? And that's what the horizontal asymptote tells you. So there's two ways we can approach this. We can take a look at the degrees of the numerators. We have degree 2 and a degree 2. If this numerator and denominator have the same degree, remember we divide the leading coefficients. 2 divided by 1 would be 2. So for 17 part A, this function here would have a horizontal asymptote at 2. Now why is that important to know? That's what the function approaches as x approaches infinity. The function approaches the horizontal asymptote. So just by virtue of the horizontal asymptote being at 2, we could say the limit as x approaches infinity of this function also equals 2. Now there's another way we could approach this. We could, and this is something you would have practiced in 1050, 2x squared divided by x squared minus 4. Now the 2x squared on the inside has to have a 0x and a 0 to make the division possible. X squared goes into 2x squared twice, and then 2 times x squared there is 2x squared, and then 2 times negative 4 is negative 8. Draw the line, switch the sign, so that's minus, that becomes plus. So cancel, there's nothing there. We have 8 as the remainder. So it's plus 8 over x squared minus 4. So what we just done is rewritten the original expression. Instead of 2x squared over x squared minus 4, it becomes 2 plus 8 over x squared minus 4. And then if we consider the limit as x approaches infinity of this function, well, what we have, if we were to plug infinity in for x, all that means is x just becomes a larger and larger value, which in turn you square it, so the denominator as a whole is just getting larger and larger and larger, but the numerator stays 8. So it's a static or a fixed value of 8 divided by a number that's getting bigger and bigger and bigger. So 8 divided by 10, 8 divided by 100, 8 divided by 1,000, 8 divided by 1,000,000, 8 divided by 10 million, 8 divided by 1,000,000,000. All of those values are getting smaller and smaller and smaller. If we continue that process, this whole fraction right here would approach 0. It would become so extremely small, 8 divided by 10 trillion by 400 trillion, then it would just become so small that it's essentially 0. The only value left then is the 2. So by that process, the limit as x approaches infinity also equals 2. So however you want to think about that one, you can think about it as far as the behavior of the graph as x approaches infinity, f of x approaches the horizontal asymptote, which is 2, or you can do a simple algebraic approach like we did here. Now for part B, x approaches 2 from the right. Now 2 is a special number in this function because it represents a vertical asymptote. If we were to rewrite this denominator, particularly when we factor, we get x minus 2, x plus 2. So if we're considering 2 right here, that means we're approaching a vertical asymptote, and we're approaching the vertical asymptote from the right. Now if you recall, I'm just going to draw a general graph. We have a vertical asymptote at 2 and negative 2. If we're approaching the vertical asymptote from the right, if you recall the graph of a rational function, when you approach a vertical asymptote, you have one of two choices. Either the graph goes up to positive infinity, or the graph goes down to negative infinity. Those are your two choices. So we've got to figure out, as x is approaching 2, are the values getting bigger and bigger and bigger up to positive infinity, or are the values getting smaller and smaller and smaller towards negative infinity? So good way to tell is just to do a quick table of values. So we need values that approach 2 from the right. So 5, 4, 3, 2.5, for example. Now, if x is 5, we get 5 squared, which is 25. 25 times 2 is 50, so we have 50 in the numerator. 5 minus 2 is 3. 5 plus 2 is 7, so that's 50 over 21. If x is 4, let's see if we're going to 4 squared, which is 16. 16 times 2 is 32. 4 minus 2 is 2. 4 plus 2 is 6. That's 12. 32 divided by 12. Okay. Now 50 divided by 21, that's a little more than 2. 32 divided by 12 is a little more than that. It's 2.6 maybe. Now if x is 3, let's see, if x is 3, 3 squared is 9 times 2 is 18. 3 minus 2 is 1. 3 plus 2 is 5. 18 divided by 5. Well, let's see, 18 divided by 5. That's a little more than 3. So the main story here is that these values are increasing. 50 over 21, 32 over 12, 18 over 5, those values are increasing. So as the x values are getting closer and closer to 2, the y values are growing and getting bigger and bigger and bigger. What that tells me is as x approaches 2, the y values are getting bigger and bigger and bigger. So if we continue to approach 2, 2.4, 2.3, 2.2, 2.1, those values would just become larger and larger and larger. So we're approaching positive infinity. Okay, question 18 refers back to the function in question 17. So f of x equals 2x squared over x squared minus 4. That's the function that we're ultimately going to be taking derivatives of, graphing, all that fun stuff. So for part A, we need all the asymptotes. Vertical asymptote. Vertical asymptotes come from the denominator. If we factor the denominator, we would get x minus 2 and x plus 2. Vertical asymptotes, if you recall, occur when the denominator is 0. We can't divide by 0. That's why the vertical asymptote is there, to prevent the graph from crossing through those x values. So x would equal 0, or the denominator would equal 0 when x is 2 or negative 2. So we're going to have vertical asymptotes at x equals positive 2 and x equals negative 2. Horizontal asymptote depends on the degree of the numerator and the denominator. If you look at our function, The numerator is degree 2, it's an x squared. The denominator is also degree 2, it's an x squared. When the numerator and denominator are equal degree, then you divide the leading coefficients. So in this case, 2 divided by 1. So the horizontal asymptote is the line y equals 2. I'm going to kind of separate this. I know I'm going to have very limited room, but I'm going to put the graph over here. I'm going to go ahead and at least put the parts that we've identified in part A. So vertical asymptotes at -2 and +2, and a horizontal asymptote at +2. Now part B, find all intervals in which the function is increasing and decreasing and find the local extrema. This would come from section 3.1, 3.2. This is just the first derivative and the first derivative test. So for part B, need to find f prime of x. This is going to use the quotient rule, which is low d high. Oops, let me make sure I get that correct. The derivative of the top function would be 4x. Low d high minus high times d low all over low squared. Okay, now if we simplify that, this term right here would be 4x cubed, or rather negative 4x cubed. If we distributed there, we would get a 4x cubed as well. So those 4x cubed terms are going to cancel each other out. So then the term left in the numerator is this term multiplied there, so that's negative 16x over x squared minus 4 squared. So first derivative test, continuing to find intervals of increase, decrease, and local extrema or relative extrema, we need to find the critical numbers. The critical numbers occur when the first derivative equals 0 or when the first derivative is undefined. Now since we have a rational function here, the first derivative would be undefined when the numerator is, or sorry, when the denominator is equal to 0. The denominator is going to equal 0 when x is 2 or negative 2. So critical numbers are going to be x equals plus or minus 2 so far. And then a rational function such as this one, if we set it equal to 0, a rational function equals 0 only if the numerator is equal to 0. And in this case, the numerator equals 0 when x is equal to 0. So those are my critical numbers. If I plot those on a number line, and then tested test values, I could do a test value right here of -3, -1, +1, and +3. Those could be my test values. Now the nice thing about the denominator, let's go back over here to the function. The nice thing about the denominator is no matter what happens inside of the parenthesis, it's always going to be squared. And whenever you square any value, even a negative value, anything squared is going to turn out to be positive. So in this particular first derivative, the denominator is always positive. So it just depends on what the numerator is. If I tested -3, for example, -3 in for this x is going to be a negative times a negative, which is a positive. And remember, the denominator is always positive. Positive divided by positive would give me a positive value there. If we test a -1 as a test value, again, for this x, I'm going to get a negative times a negative, which is a positive, and a positive divided by a positive is positive. Now, if we tested +1 right here, -16 times +1 is -16, so negative divided by a positive is negative. And then if I tested +3 right here, Negative 16 times 3 is negative. Negative divided by a positive is negative. So the only time we have switching from increasing to decreasing or vice versa is right here. So the graph switches from increasing to decreasing. Now, intervals of increase are these two intervals right here. Now, -2 isn't in the domain of our function. If x equals -2, if you go back up to the original function here, if x equals -2, the function isn't defined. So I'm not simply going to say that the function is increasing all the way from here to here. I'm going to separate this into two intervals, from -infinity to -2, and from -2 to 0. It's decreasing similarly from 0 to 2 and from 2 to infinity, and there's a local, turns out to be a local maximum right here. There's a local max at the point 0, and if you plug 0 into the original function, it would turn out to be 0. So there's a local max at the point 0, 0 right here. If we can start piecing this graph together, in order for this point right here to be a local maximum, the graph has to be decreasing on the left side of it, or rather increasing on the left side of it, so it's increasing up to that point, and then it's decreasing. So it looks like we have an upside down parabola. And continuing here, the graph is increasing from -infinity to -2. -2 is just our vertical asymptote right there. So the graph is increasing as it approaches -2. And then over here, it's decreasing as it moves away from 2, +2. So we'll get back to that behavior on the graph here in a second, but let's do part C, which is the second derivative. Now this one's going to be a lot to keep track of, so we need, again, the quotient rule. Which is low d high minus high d low. Now this is going to require the chain rule, because this bottom piece of the first derivative here has an inside function and an outside function. So the chain rule says do the outside function first, which is dropping down the exponent and then decreasing the exponent by 1, and now we need the inside function, derivative of the inside function rather, which is 2x. So we've got low d high minus high d low all over low squared, so this is going to be x squared minus 4 squared squared, so that's going to be to the 4th power. If you're squaring something that's to the 2nd power already, that means it's raised to the 4th power. Now simplifying some terms in the numerator. Well, let's write the denominator, x squared minus 4 to the 4th power, and that's a minus right there. If we consider this minus sign in the numerator, separating the numerator into a left and a right side, the left and the right side both have an x squared minus 4 in common. So I can factor out an x squared minus 4. And they also have a negative 16 in common. So I could factor out the negative 16 as a common factor. So that would leave, on the left side here, if I've taken out a negative 16 and one of the x squared minus 4s, that leaves an x squared minus 4. And then I took out this negative 16 already. And I've taken out this x squared minus 4. This 2x and this 2 and this negative here and this x right here. So let's keep track. Let's try this again. So we've got this 2x, we've got this 2x, and we've got this negative. That's all going to multiply together to be negative 4x squared. Now, this x squared minus 4 can cancel with one of the x squared minus 4s in the denominator. And then here inside the parenthesis can all be simplified to negative 4, rather negative 3x squared minus 4. And since both terms are negative, I can factor out another negative. I can factor out a negative sign. And that negative 16 is going to become a positive 16. So we would have positive 16. Remember, this x squared minus 4 canceled with one of the terms in the denominator. Inside, I factored out this negative, so it will become 3x squared plus 4 all over x squared minus 4 cubed. Okay, so there's our second derivative. We need to find intervals in which the function's concave up and down and inflection points. So this is kind of like the first derivative test for finding intervals of increase and decrease and relative extreme. We need to figure out where the second derivative is equal to 0 and where it's undefined. Now, again, we have a rational function which only equals 0 when the numerator equals 0. No matter what we plug in for x, whether it's positive or negative, whatever we plug in for x is going to be squared, which means it's positive. And then you multiply it by 3, which is positive, and then you add 4, which still makes it positive, and then you're going to multiply it by 16, which still keeps it positive. So regardless of what x equals in the numerator, even if x is 0, you're going to get a positive value. So what I'm saying is this function here is never going to equal 0. But we can also check to see where it's undefined. And right here, the denominator of a rational function is where we would have undefined values. So x squared minus 4 is going to equal 0 when x is positive or negative 2. So if we do a test for concavity, negative 2, positive 2, and then choose test points, negative 3, for example, is a test point. If I plug negative 3 in here, I'm going to square it to get 9. 9 minus 4 is positive, to the third power is positive, so we're concave up when x is less than negative 2. Now in between negative 2 and 2 is 0. If I plug in 0 for this x and square it, I get 0 minus 4, which is negative. Negative to the third power is negative. And remember, the numerator here is always positive, so a positive divided by negative is negative, so the graph is concave down between negative 2 and 2, which we already see right here. We've already graphed a piece of the graph between negative 2 and 2, and it is concave down. And then if I choose a test point on this interval, 3 for example, and plug it in for that x, 3 squared is positive, minus 4 is still positive, to the third power still makes it positive. The numerator is always positive, so a positive divided by a positive is positive. Normally when we have switching of concavity like here, we would say that's an inflection point. So again, normally we might say that, okay, there's an inflection point here when x is -2, and there's another inflection point here when x is +2. But if you recall, -2 right here and +2 are not part of the domain. That's why we have vertical asymptotes there. So there actually are no inflection points, even though it does switch concavity. What it means is it just switches concavity as you reach a vertical asymptote. Okay. Now, part D, sketch the graph. Be sure to find the intercepts. We've already found one intercept right here. That's an x-intercept of 0. It's also a y-intercept because it's right at the origin. So, going back to the original function, to find a y-intercept, you let all x's equal 0. If you let all these x's equal 0 in this original function here, you're going to get 0 divided by -4, which is 0. So the y-intercept is 0, which we already knew. X-intercepts occur when y equals 0. Well, another name for y is f of x. So f of x is going to equal 0. Remember, when you have a rational function, the function only equals 0 when the numerator is equal to 0. So the only x-intercept we're going to have is also x equals 0. So this is the only x-intercept. Okay. Now, the piece of the graph here on the left of -2, we know it's concave up because of right here, and we also know it's increasing because of right here. So it's concave up and increasing, and we have to make sure we have this horizontal asymptote here at y equals 2 when we have this vertical asymptote at -2. So remember, when a function approaches an asymptote, it either goes up to infinity or it goes down to -infinity. And the end behavior has to near this horizontal asymptote. That's why I'm drawing it either like this or like that, because the end behavior has to approach that asymptote. Now, if I were to say, okay, well, maybe it looks like this and it approaches -infinity, well, first of all, this graph decreases and it's concave down, so I know it can't be that. So it has to be this right here, because that's the only graph that would be increasing and concave up. Now this part of the graph right here, if you recall from part C, it's still concave up, but from part B, we know that it's decreasing. So if we were to draw, let's say we were going to draw, okay, maybe it looks something like that. Well, yeah, that's concave down and increasing, so that's actually backwards. We need it to be decreasing and concave up, which would be something like that. That's a decreasing concave up piece of the graph.
So the average cost, again, C bar is equal to C over X, which is going to be 0.75 plus 4,000 over X. Now the value of the average function at these two specific X values, for X is equal to 100, we're going to have 0.75 plus 4,000 over 100, which is 40, which equals 40.75. Now, if we go back and take a look at the cost function, they have a pretty small unit cost, per unit cost. It's 75 cents per unit, but they have a pretty large initial cost here of $4,000. So they're not producing very many with X equals 100. And because of such a high initial cost, their average cost is going to be rather high, but as they start to produce more, so for X equals 1,000, okay, this is 0.75 plus 4,000 divided by 1,000, which is 4, so you can see that dramatically reduces the average cost per unit of producing that commodity. So as they continue to produce more and more and more, the average cost is going to continue to go down, but it's only going to go down up to a certain point, and this was our discussion on limits to infinity. And that's the next question here. Determine the limit of the average cost function as x approaches infinity. So the limit as x approaches infinity of 0.75 plus 4,000 over x. This is equal to the limit as x approaches infinity of 0.75 plus the limit of 4,000 over x. Now the limit of a constant is just that constant. And the limit as x approaches infinity of this, as x continues to get larger and larger and larger, beyond 4,000 to 4 million and 4 trillion, this is going to result in a smaller and smaller and smaller fraction, and as x approaches infinity, this fraction approaches 0, so the limit is 0. 0.75 plus 0 is 0.75. Now, the question asks you to interpret this in the context of the problem. They're obviously not going to be able to produce an infinite number of this, but they're not going to be able to produce or produce enough to get an average cost lower than 75 cents. 75 cents is the limit of how low their average cost can go. That's how you would interpret that. Okay. Last one. The cost for the federal government to seize P% of an illegal drug as it enters the country is modeled by this. P has to be between 0 and 100. Now the way that this is set up, we can use the percent of P as the actual number, because P is between 0 and 100. So we don't actually need to change these to decimals. We can use 25% as the number 25 and 50% as the number 50. So the cost, so for $25, or for 25%, if these federal agents or whatever they are want to seize 25%, then according to this model, it's 250 times 25 all over 100 minus 25, which is 75. And then 25 over 75. If you take a look at this, 25 over 75, there's just 1 over 3. So this is 250 thirds, which is roughly 83, I think it's 83.3. Keep in mind this is in millions of dollars, so if they want to seize 25% of this illegal drug, it's going to cost them a little more than $83 million. Now, if they really up their efforts and are aiming for 50%, that follows the model 250 times 50 over 100 minus 50, which is 50. Now, these two values are going to cancel out, so that's $250 million. So they increase their efforts, they double their efforts, but their costs more than double, up to $250 million. So we're seeing a pattern here. If they increase again, that's going to be 250 times 75 all over 100 minus 75, which is 25. 75 over 25 is 3. 250 times 3 is $750 million. So now, once they go much more than this, 80%, 90%, 91%, 92%, these costs are going to increase similar to an exponential increase. As their efforts are reaching 100% of this illegal drugs to be seized, what's the value of this side going to eventually start to reach? This is another idea of a limit at infinity. So what they're asking is find the limit as C approaches, or as P approaches 100 from the negative side. So limit as P approaches 100 from the negative side, 250 P over 100 minus P. Now, this is not meant to be done analytically. We've done a numerical analysis kind of here, where we've tested some points. If we consider just a rough idea of what this graph might look like, there's a vertical asymptote at 100. So these are tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 90. So we have a vertical asymptote at 100. And these represent percentage points of how much of the drug they want to seize. So at 25%, which was about right here, they were at 83 million. At 50%, they were at 250. At 75%, they were way up here. So the costs are going to, as the graph approaches this vertical asymptote of 100, where's the graph heading to? And the answer is it's heading to positive infinity. So the answer to this is infinity.
Okay, number 21, given the polynomial function x plus 2 times x minus 2 to the third power, which if you were to multiply out equals x to the fourth minus 4x cubed plus 16x minus 6. We got to find where the function's increasing, decreasing, local extrema, intervals, concave up and down, inflection points, sketch the graph. So a lot going on here. Part A, intervals in which the function is increasing and decreasing. Find the local extrema. That's the first derivative test. Now, it may be easier to take the derivative of this part of the function, or that form of the function. Let me write that down. It would be, if I can write here, f prime of x would be 4x cubed minus 12x squared plus 16. See, the problem with this is, though, we would need to set this equal to 0 and try to find the zeros, or try to solve it. It's kind of hard to do. That's not easily factorable. So rather than taking the derivative of this form, even though it's going to be a little harder, I can take the derivative of this form. The reason being, it may end up being easier to factor at the end. So that's a product rule. If we consider the product there, this would be like an f, and that would be a g. So the product rule is f prime, which is 1, f prime g plus g prime. Remember, that's a chain rule, so there's g prime times f. So now we look for common factors between the left and right side. That plus sign right here separates the problem into a left and a right side. So the left and right side both have an x minus 2 squared factor. That leaves, from the left side, that would leave an x minus 2. And from the right, that would leave a 3 times x plus 2. Simplifying this expression inside is going to be 4x. That's going to be 6 minus 4x plus 4. Looks like I forgot the squared right there. Don't want to do that. Now set this equal to 0, and we would get critical numbers at x equals 2 and x equals -1. Now when we put those on a number line for our first derivative test, and test some values. In this region, for example, we could test -3. -3 right there for x. -3 minus 2 is -5, but -5 squared is positive. And then -3 for that x makes -12 plus 4 with a -8. Positive times a negative is a negative. Matter of fact, regardless of what we put into here, we're going to be squaring it, so that's always going to turn out to be positive. So we really just need to figure out what's happening with that factor. So if I plug in a test point in this interval, 0, for example, If I plug in a 0 right there for that x, I'm going to get a positive. Positive times the positive is a positive. And then if I plug in something to the right of 2, like 4, that's also going to come out to be positive there. So positive times a positive is a positive. So it's increasing on both of those intervals. So from -1 to infinity, increasing. From -1 to infinity, it's decreasing on the interval -infinity to -1. And since we have switching from decreasing to increasing there, that's going to be a relative or a local minimum at the point -1. And if we plug -1 into the original function, -1 into the original function there, -1 plus 2 is 1. -1 minus 2 is -3. -3 cubed is -27. So -1 comma -27 would be a relative min. Okay, so for part B, we're going to need intervals in which the function is concave up, concave down. That means we're taking a second derivative, so we could take the derivative of the first derivative there. I think, however, I'm going to go back to this form of the polynomial. The first derivative was, so f prime of x was 4x cubed minus 12x squared plus 16. The second derivative of the function would then be 12x squared minus 24x. So then that's pretty easy to solve for 0. If we set that equal to 0, take out a 12x, that's going to leave x minus 2. So then we're going to have x equals 0 and x equals 2 there. Now if we use test points in each of the intervals, something here to the left of 0 could be like -3. That's going to make a negative here and a negative there. But a negative times a negative turns out to be a positive, so that piece of the graph's concave up. Test point in that interval could be 1. That makes a positive and a negative, which is negative. So that portion of the graph between 0 and 2 is concave down. And then a test point or a test value in that interval could be 3. That makes a positive and a positive, which is positive. So it's concave up on the intervals -infinity to 0 and 2 to infinity, and it's concave down on the interval 0 to 2. And because we're switching concavities here and here, we're going to have some inflection points. At the point 0, comma something, and 2, comma something. So going back to the original function, if we plugged in a 0, we would get -16. And if we plugged in a 2 into the original function, we would get 2 minus 2 there. That would be 0. So it's 2, comma 0. So those are the inflection points. Now, graphing the function. Let's try that again. Get some straighter lines there. Okay. This does not have any vertical or horizontal asymptotes because it's not a rational function. It's a polynomial function, so it's smooth and continuous. We have a relative minimum value at -1, comma -27. So, I mean, that's way down there. Oh, one other thing we need to find before we graph this are intercepts. So coming back to the original function here. Intercepts are going to be -2 and +2. The x-intercepts, rather. And we're going to have a y-intercept at -16. So let's see, here's my local min. And let's say that that's at -27. Let's say that the y-intercept there is at -16. And considering the degree of this polynomial, it's degree 4. Even degree polynomials have end behavior that are going in the same direction. And since the leading coefficient is positive, I know that the left side is going up to infinity. And the right side is also going up to infinity. Okay, so the graph needs to be decreasing because of here it's decreasing from -infinity to -1. So if I continue tracing the graph here, it's decreasing from let's try that again, decreasing from -infinity to -1. Then it starts to increase from -1 to infinity. So it's increasing the whole way. Does that just mean it's a straight shot? No, because we have some inflection points and concavity to consider. It needs to be concave up from -infinity to 0. So -infinity to 0. So we're concave up there. Then it switches to concave down. So then it kind of has a downward curve like this. So it switches to concave down from 0 to 2. And then it goes back to concave up. So I got my minimum value down here, -1,27. There's an inflection point here where it switches concavity. There's an inflection point there where it switches concavity. So there's the graph.